Okay, so today we're going to get into protein structure. So we'll start out with an overview of the different levels of protein structure, and then we'll talk about the actual peptide bond, its properties, and the primary structure, and then we'll get into three types of secondary structures and what they are. All right, so if you remember back, I guess it was the first lecture where we're talking about the structures of biologically important macromolecules and assemblies. How do they attain these structures, and what unique properties and functions do they allow? So we just looked at the amino acids, and we looked at their basic structure and their side chains, these building blocks of proteins. So we want to now be able to understand, as they come together, what is it about the structure of the amino acids that contribute to the various levels of protein structure, all right, and how are they being stabilized? All right, so for those of you who might not know, a protein, all right, is a linear polymer of amino acids. They're linked to one another by peptide bonds, all right, and we'll talk a little bit more tomorrow about actually how you go from a gene to a protein. And for in terms of looking at a protein and its structure, we can actually discern that there are four levels of protein structure. So there's a hierarchy. So the primary is just the linear sequence of amino acids. So this is simply if you took amino acid 1, hooked it up to amino acid number 2, hooked that up to amino acid number 3, etc. And those are covalent bonds. The covalent bond is the peptide bond. So linear sequence of amino acids, nothing really having to do with structure per se. We call it primary structure. You could also call it primary sequence. Secondary structures, all right, this is the first higher level where you start to develop some structure. And with secondary structure, these are localized structures. So amino acids that are close to one another in the primary sequence, they can adopt a localized structure, right? The first organized structure above simply the linear sequence. These types of structures, when we look at them, you'll see that the way in which they are stabilized are through hydrogen bonds with backbone atoms. So secondary structures are not being stabilized by any hydrogen bonds involving the side chains. Right? These secondary structures, when they are formed, all right, it's strictly because of stabilization with hydrogen bonds of the peptide backbone. All right? If that wasn't the case, then you could not have all of the amino acids potentially in the different types of secondary structures, if there was a requirement for certain side chains to be there. So secondary structures, when we look at them, hydrogen bonds that are stabilizing it are coming from the backbone atoms, and we'll look at that. The 3D structure, the tertiary, is the folding of these secondary units. So once you have these localized secondary structures, they're going to start to fold together. What you're doing here is you're minimizing volume, you're getting packing. We'll talk some more about what's going on in terms of stabilizing the 3D structure. We know in this instance we get side chains that are now contributing hydrogen bonding to stabilizing it. Right? What else do you think is going to stabilize that? We mentioned it. The hydrophobic effect. Okay? So primary structure, just the sequence. Secondary, localized structures, hydrogen bonds coming from the peptide backbone. As it starts to fold up to give you a 3D structure, then you're getting the hydrophobic effect coming in. You're getting side chain contributions now. Quaternary structure. A single polypeptide chain does not have quaternary structure. All right? If you have a single polypeptide chain and it folds into a three-dimensional structure, that is at this level. Quaternary is where you get multiple polypeptides coming together. So when we talk about hemoglobin, we'll see a case where you're getting 4 different subunits that are coming together. They each have their own 3D structure. They come together to form a multimeric protein or a protein complex. And we'll see what the consequences are of having multiple subunits to an enzyme. Okay, 4 levels. So depicted like this. The primary structure is just the sequence. Hydrogen bonds involving just the main chain. The backbone will give you a secondary structure. Here in this case we're talking about an alpha helix. This is a localized structure that's contained, let's say, within here. Now you're getting a three-dimensional structure that is coming about by folding of all of these secondary units. Hydrophobic effect is going to contribute, bearing things to the inside. Hydrogen bonds, bless you. And then when you have multiple subunits coming together, that is quaternary. So when you look from left to right, you're going from something that's more extended to more compact. This is more disordered, more ordered. All right? Okay, so let's start with the peptide bond. It's an amide bond, so let's say here we have 2 amino acids that are going to come together to give us a dipeptide. So we have glycine here, alanine, amino acids. Here is the amino group. Here's the acid group. Here's the alpha carbon. You have a hydrogen, and the side chain of glycine is a hydrogen. Here you have alanine. This is the second amino acid, the amino group, the carboxyl group, the alpha carbon, the hydrogen off the alpha carbon, and the R group in this case, which is a methyl group. This reaction, all right, is a dehydration reaction. You're getting the elimination of water, and if you look at this, these are both zwitterions. So you have a positive charge here, a negative charge there. You have a positive charge there, a negative charge there. When you get that condensation, then this is the peptide bond. You have a negative charge still at the C terminus, a positive at the N terminus, but these charges are going away during the formation of the peptide bond. All right? This bond, and you'll see it in a lot of the figures, you have this shaded area. What is that meant to imply? It's planar, all right? When you look at these peptide bonds, if you draw this out, you don't have to worry about all of these angles, and we're also going to talk a little bit about rotations. You don't really have to worry about that. We're really mostly interested in terms of understanding, you know, how the proteins come into being, what their structures are with respect primarily to the things that are contributing to its function. So that would be its the hydrogen bonds and hydrophobic effect and so forth in terms of stabilizing it, and then how charges allow it to interact with substrates. This is planar. When you look here, the reason that this is planar is that this oxygen, carbon, nitrogen, right? Here is the peptide bond. This bond and this bond both have partial double bond character. Why? So let's say this is the carboxyl group that came from the preceding amino acid, and then this is the next amino acid coming in. So here's the peptide bond. Is nitrogen more electronegative than carbon? All right. It's not as electronegative as oxygen, but it has the ability to pull electrons this way. So in fact, if you have this carbon and you have a double bond here, these electrons can delocalize to some extent between the oxygen and the carbon and the nitrogen. So that amide bond, that peptide bond, has partial double bond character. So if you then envision that these electrons can be delocalized over those three atoms, right, that is really what is causing the planarity, the rigidness between those three atoms being on the same plane. If you look at the bond length, all right, if you have a carbon and nitrogen with a double bond, that's 1.27 angstroms. When you look at a normal amide bond between a carbon that's part of a carbonyl group and a nitrogen, that is 1.32 angstroms. A normal alpha carbon nitrogen bond is 1.46. So this here, which is the amide bond, that is intermediate, right, between a simple carbon-nitrogen bond and a double bond between carbon and nitrogen. So that shows that that does in fact have partial character. You don't have to worry much about these specific numbers. The important thing here is understanding where the peptide bond is, that when you look, right, if this is a polymer, then as that polymer goes down the line, you've got different R groups, right, depending upon what amino acid is coming in, which ones are there. But what is the constant? The constant is this backbone chain when we talk about main chain atoms. And the hydrogen bonds that are going to stabilize the secondaries, if they're coming from the main chain, where are they? Which atoms here? This nitrogen is electronegative, so it's going to be pulling electrons this way. So the amide hydrogen is going to be slightly electron deficient. So that's going to be kind of a delta plus. The carbonyl oxygen of the peptide bond is what? Slightly negative. So these secondary structures, they are being stabilized only by hydrogen bonds involving the main chain atoms, and they're only carbonyl oxygens and the amide hydrogens. And we'll see what those look like. Okay, you don't really have to worry too much about the geochemistry. Here's the peptide bond right here, that blue bond. That has to stay planar. These three atoms have to stay on the same plane, but you could get rotation where in this case, this amino acid here, there's the alpha carbon, there's its R group. The next amino acid, its R group, is in this direction. So that is referred to as the trans configuration. The two R groups are on opposite sides of the peptide bond, whereas if you got rotation and brought this up, right, or this one down, that in this configuration, you still have planarity of the peptide bond, but both R groups are projected in the same direction. And what would be problematic with that? Steric hindrance, in most cases. So trans is the preferred configuration. In fact, when you have these, when you look at the peptide bond and these possible rotations that can occur, here and here, you can't have every you can't have every possible situation in terms of where they are. In other words, there can be, you have to avoid steric hindrance, excuse me, but there are certain restrictions that are put upon the geometry, and basically if you do the math, you don't have to worry about this, but when you do the math and you do the computer modeling, it actually turns out that there are specific angles on those flanking bonds that can occur and other ones which are restricted. And so just so that you know this Ramachandran plot, that basically what you're plotting are these two angles versus one another and asking what are the possible combinations that in theory can exist in nature, and you get these whiteout areas. And when you look in those areas, that's where we see, okay, the known secondary structures such as the beta sheet and the alpha helix, which we'll go over in a second. You don't have to worry about this. Okay, so a little bit about the stability of peptide bonds. Here, if we take a dipeptide, glycylalanine, glycine hooked up to alanine, we put it in water to hydrolyze back into the two amino acids. The delta G for that is what? It's negative, so what does that mean? It's favorable. So if the hydrolysis is favorable, then the formation must be energetically unfavorable, right? So in protein synthesis, you're taking a situation where the delta G, when you look at bringing these two amino acids together, the formation for every peptide bond, that's energetically unfavorable. So you're going to have to link that to some other reaction which is energetically favorable so that the overall net energy change is favorable, right? That's what happens during protein synthesis. We're not going to get into that too much, but you need to appreciate that energy has to be put into making these bonds, and that an easy way, and we'll have some cases where you'll look and we'll talk about particular proteins and their composition. What amino acids are there? They're rich in this amino acid, rich in that amino acid. In the old days, before we actually got to the point where the genes were cloned, so we could look at the sequence and say we know exactly what the sequence is. In the old days, if you had a protein and you simply wanted to say what's the amino acid composition, you could take that, put that in acid, heat it up, and every peptide bond would get hydrolyzed. So you're breaking the protein down to all the free amino acids. You could run those out, analyze them, and say we've got 10% this amino acid, 20%, 5%, whatever it is. Okay? All right. We'll talk more about reverse genetics tomorrow, but known proteins, they can be relatively small or very large. The sequence of the amino acids is coming by the sequence of the gene, right? So through transcription and translation, you've got a particular gene, it's being transcribed into messenger RNA. The gene has the beginning, a middle, and an end. The messenger RNA has the beginning, the middle, the end. The beginning of the messenger RNA is translated to give you the beginning of the protein, the start of the primary sequence. The first amino acid, the amino terminus, to the C terminus, all right? So all of the information is there, and if you know that sequence, right, then you can deduce the protein sequence. And there are even models now where if you have the DNA sequence to the protein sequence, you can take the protein sequence in, and with software that's available, you can actually start to predict not only secondary structure, but three-dimensional structure and potentially function. Why? What dictates function? Right. Okay. So we said that secondary structure, by definition, is a localized spatial arrangement of amino acids. They're near one another in the primary sequence. If you've got an amino acid that is 200 amino acids from another one, and there's some kind of an interaction, they are not interacting at the level of secondary structure, right? They're interacting at the level of tertiary, okay? So, localized structural units. They usually require that those R groups be in the trans configuration, and this is what we're talking about in terms of the stability. So here is the carbonyl oxygen from one amino acid, and here's the amide hydrogen from another amino acid. These two amino acids in the primary structure are close together. Okay, so the first one is the alpha helix. Okay, so the first thing is it's a right-handed corkscrew. There are right-handed helices, left-handed helices. The alpha helix being right-handed, who has trouble envisioning what that is or what it means? This sequence, it has a beginning and an end, right? In other words, the polypeptide chain is going from what was early in the gene sequence to later. So in this case, it's coming like this, down. If you were at the base of a stairwell and you were going to go up the stairs, one possibility is as you start to rise and take your first step, you're either going to move to your right or you're going to move to your left. Right? Either the stairs are going to go counterclockwise as you go up, or they're going to go clockwise as you go up. The right-handed is going counterclockwise as you go up. Okay, one turn about every 4 amino acids, 3.6 residues, right? So that if you have an R group here, you come around, and when you get to the same position, right, as you make one full turn of the helix, you're going 3.6 residues. Again, we're getting structure being stabilized. It's a secondary structure, so the atoms involved are main chain, right? And in this case, you have, let's say here is a nitrogen, part of the amide bond, the peptide bond. Here is the hydrogen, and it is hydrogen bonding with this oxygen, which is part of this amino acid, which is 4 away. Right? So the hydrogen bonds involved this carbonyl oxygen of residue N, and then as you go around the helix a little bit more than one turn, the amide hydrogen of residue N plus 4. So you see these dashes. Those are all hydrogen bonds that are stabilizing the helix, and all of these hydrogen bonds are in the same axis as the helix. Okay? When you look at the R groups, they turn out to be all projecting out away from the helix. We talked about proline. I think I mentioned it early on, that proline, because of its structure, it does not have an amide hydrogen, right? It's cyclic. So that is going to destabilize a helix because you're losing a hydrogen bond, and also puts a kink in because of the ring structure. But when you look at an alpha helix, you can look at it in this configuration. But let's turn it on its side and look down the axis. Right? We're looking from the top or from the bottom. Look over here. So all of these R groups are projecting out. So to take kind of a simple view of this secondary structural unit, you're basically looking at a cylinder. And that cylinder is going to have these projections of the side chains. So let's take an example here of some amino acid sequence. The sequence is a localized sequence. It's a secondary unit. And what this is called is a helical wheel. So let's say this is amino acid 1, 2, 3, 4, 5, 6, 7, 8, right? When you do that and then you tilt the cylinder and you look at the cylinder and you say, all these R groups that are projecting out, what do I see? A lot of times what you see is something called an amphipathic helix. That about every fourth amino acid here has kind of a similar property, so that these here in yellow, what do they have in common? They're nonpolar, whereas on this side, they're polar. So an amphipathic, right? Something that's amphipathic is one molecule that has two different properties. So in this case, this alpha helix is a cylinder that's coated, let's say, on one side, because of the periodicity of the side chains, is hydrophobic, and this side is hydrophilic. So what would be a reasonable explanation for that? Right. So if you have a helix and you're actually using that helix to stabilize, then this hydrophobic region here is going to be nuzzling up with other hydrophobic residues towards the inside. The driving force for that is, hydrophobic effect. The driving effect for the hydrophobic effect, is it enthalpy or entropy? Entropy of water, all right? So we can keep going back. Those earlier lectures do have a purpose, right? So this amphipathic helix then allows you to see how you can take, as you're building three-dimensional structure, right? Let's take a step back. If you've got DNA and it has a particular sequence, that particular sequence codes for a linear polymer of amino acids. You're going to go from that to a three-dimensional molecule, okay? But all that information is there. All the information for that structure, the three dimensions, is there in the DNA, because the DNA gives rise to that linear sequence of amino acids. The linear sequence of amino acids, there are certain structures that can be adopted or not, and then when they are adopted, let's say in this case, by an alpha helix, then you see that the particular sequence, it's not like, well, we're going to have a string of hydrophobics and a string of polars. It's actually, we're going to have a hydrophobic and a hydrophobic, and then a couple of hydrophilic, and then back to a hydrophobic. So that sequence, as it folds, is going to give certain properties to the structures. And then once you have this structure, then this part of the helix is going to say, what am I supposed to do? I'm going to look for other hydrophobic things to bury to help out the water. And so the whole folding process, I mean, there are some exceptions to this where there are other proteins that help certain proteins fold properly, but for the most part, all of the information for that whole 3D structure is there in the DNA. Okay? Everybody good with that? The computer's not. Okay. So let's go to a beta sheet now. Remember, a beta sheet is a secondary structure. So we're talking about atoms, we're talking about amino acids that are close in the primary structure. So this beta sheet, we see here this main chain, this backbone, right? Here is another one, right? Those are not two different polypeptide chains. It's the same polypeptide chain, which is going in one direction and then turns around and nuzzles up to itself, right? It's a more extended structure than the alpha helix. You'll see that or appreciate that better in a minute. The hydrogen bonds here exist between the adjacent beta strands. So in the helix, you have the helix, and the hydrogen bonds are projecting, right, in the same axis as the helix. Here, the hydrogen bonds are going across between the two strands. So when we talk about a beta sheet, we will talk about a strand. So this would be a two-stranded beta sheet. It's not a two-polypeptide beta sheet, right? If it was two polypeptides, we'd be talking about quaternary structure. These are localized structures, secondary structures. So these are two strands. The side chains. In the helix, all the side chains are pointing out. In a beta sheet, you'll see this better in another figure, they're alternating up, down. So, for example, here, of course my pointer's going to go out. Here the R group is coming up, down, up, down, up, down. Okay? So if we look at the alpha helix side by side with the beta sheet, so in this case we're looking at, let's say, drawn to scale, so that we've got a beta sheet next to an alpha helix, the same distance. If you count the amino acids, count the R groups, R1 is here, R2, R3, R4, R5, R6. So there are 6 amino acids here in the length of that beta strand, whereas over the same distance in an alpha helix, there are 9 amino acids. So the alpha helix is a more compact structure, and also you would have more R groups within that distance. All right, so beta sheets, if they have multiple strands coming together and hydrogen bonds within the strands, there are 2 ways in which that can occur. The first is anti-parallel. When we talk about a polypeptide chain or a portion of that chain, does it have an orientation to it? It does. The gene has a beginning. Your information has a beginning. The very first amino acid, right, to make the protein is the amino terminus, right? You've got the amino terminus, the carboxyl group, that peptide bond forms, and now you have amino C terminal. You bring another one, amino C terminal. So the beginning of a protein has a free amino group. The very end of the protein has a free carboxyl group. So there is a polarity. There is an arrowhead going from beginning to end, alpha, omega. So in this anti-parallel configuration, what you have is going N to C. That means that you're going this way, right? And in this figure that's in the notes, don't get confused. In this case, there are no R groups, right? So we're just talking, right, about main chain atoms so that you can simply look at the orientation and the hydrogen bonds that are going on. So anti-parallel, you're going from left to right, and then you're going from right to left. So in this case, you could envision that that when the chain is made, it's going from left to right, and then here maybe it kind of loops around a little bit, and then it comes back on itself this way. Right? So you have a strand, a little meandering, and another strand. Okay? Then it might come back on itself this way. So we call this anti-parallel because as the chain is going from early to late, the N terminus towards the C terminus, these are in anti-parallel directions. When you look at the hydrogen bonds, in that configuration, they're lined up better, right, as opposed to here. So the hydrogen bonds in an anti-parallel beta sheet make that a little bit more favorable than in a parallel. So in a parallel, let's say here's the N terminus, and it's coming this way, right? Now, for the second strand, it can't loop around and go like this. What this is doing is probably coming like this, and then it's meandering down here, and then going this way, all right? So these are just lining up these strands, and then you have hydrogen bonds between the strands that are stabilizing it. Question?
So these are basically just one entire protein that's lapping back on itself?
Yes, but we'll take that one step further. In terms of lapping back on itself, it's not, it's doing it in a very localized environment, right? So you don't have, let's say, in this case, amino acid number 3, 4, 5, 6, 7, 8, 9, 10, and then the protein goes around, and then you got another strand coming back which constitutes amino acid 316, 17, 18, 19, right? These are secondary structures, so keep going back to the definition. They are structures adopted by amino acids that are close to one another in the primary structure, and they're stabilized by the hydrogen bonds of the main chain, okay? But you're right, these are strands that are making the beta sheet. Now, what you'll see, I guess it will be next Tuesday, are there, well, let me show you this first, and then you'll be able to appreciate that more. So let's kind of take the kind of the kindergarten view of these structures. The kindergartner would draw a cylinder and paint maybe one side one color and another side another color. They're not always amphipathic, but when you think about what is it that the cell is trying to do with these proteins and so forth, you really have these basic structures. So if you want to have charge or functional groups put into position in the way, let's say, where you want all these charges on one side of a structure that's kind of cylindrical or circular, you're doing that with the helix. A beta sheet is exactly what it says. It's a sheet. So in this case, you have 1, 2, 3, 4. So this is a 4-stranded beta sheet. If the R groups alternate up, down, then the polypeptide will go whatever, and either comes back this way or it's coming back this way. I don't know if it's parallel or anti-parallel. I think it's actually parallel in this case. So if you just kind of take a step back, right, what is it that this structure really is? Right? It's a sheet, and really you have all these R groups projecting up in one orientation, and then a bunch of others pointing down. So they can have all the residues, let's say on one side, have one property, and all the ones on the other one. So if you had this beta sheet, and it was involved in packing, right? The sheets were going to pack, and there was going to be a hydrophobic effect involved in packing, right? Let's say you just wanted to bring another sheet down on top of this sheet. So remember, remember at the very beginning where we had a secondary structure, and then when it folds in the 3D, it can interact with other secondaries. So two helices can come together. Two beta sheets can come together. So let's say you had two beta sheets and you want them to come together. You want them to come together because you want some structure that is basically giving, let's say, negative charges out on both sides, and you want it in kind of a plane. A helix isn't going to help you. A sheet would, right? And so if you wanted to bring, let's say, two sheets together to have the right distance, you would have, how would you have the R groups configured? In terms of their properties, you might imagine amino acid, one of the strand is going to be hydrophobic, hydrophilic, hydrophobic, hydrophilic. So when you look at the sequence, you'd see this alternating in every other amino acid having the same properties. And so that when it adopts the beta sheet configuration, everybody on one side of the sheet is hydrophilic, everybody on the other sheet is hydrophobic. Then you've got another sheet from a different part of the protein where everybody on this side of the sheet is hydrophobic, everybody on the underside is hydrophilic, and those two sheets will come together. Okay? We'll see an example of that with a structural protein. But again, it's all structure dictating function and functional interactions. Okay, last one for today is a beta turn. So in a beta turn, when you think about three-dimensional structures, these are globular proteins that we're talking about now. So as they adopt a three-dimensional structure, you've got the primary structure, which is giving rise to these localized secondary structures. So for the most part, we're talking about alpha helices, we're talking about beta sheets, and then if you have sequence that's neither in a beta sheet nor an alpha helix, we would call that random coil. All right? It's not really adopting a secondary structure. Not all of the sequence in a protein is contained within a secondary structure. The important thing is when you do have secondary structure, they're usually interacting with themselves to stabilize structure, or they're on the periphery of the molecule and they're interacting with other molecules, right? They could be substrates, they could be binding partners, whatever. But as you adopt that structure, you should be able to appreciate you're going to have to make turns and bends. Random coil can allow for these flexible turns, but when you want to make a real sharp turn, you have a beta turn, which is a secondary structural unit because it involves localized amino acids, right? In this case, you've got 4 amino acids, and over the course of those 4 residues, you can get a 180-degree turn. The structure itself is stabilized, right, by a hydrogen bond between this amide hydrogen here and the carbonyl oxygen of here, N and N+3. So if it is a structural unit, amino acids close together being stabilized by hydrogen bonds from the main chain atoms, it is by definition a secondary structure. To make a quick turn like that, even if you didn't know it from the book, thinking about the amino acids that we've gone over in their structures, what would you imagine could be in there, in these turns? Proline and glycine, why? Proline is a cyclic, and we already know that introduces a kink in the polypeptide chain. You don't want it in alpha helix. But if you want to make a sharp turn, the presence of a proline there already starts you turning. It already starts you to kink. Then what is it about glycine? Lack of steric hindrance. It has the smallest R group, which is a hydrogen. So proline and glycine often found in these turns because you're going to get that quick 180-degree change of direction over 4 residues, right? And often they're going to be at the surfaces of these globular proteins, okay? Any questions? Okay, so we'll start to look tomorrow on the types of interactions, hold on, the types of interactions that are going to stabilize the three-dimensional structure as these secondary units come together. But don't lose sight of the interactions that are stabilizing these guys, okay? Make sure you understand that.
Can I ask you a quick question? You say, what if we have two beta sheet, and then let's say this side of the R group is hydrophobic and this